The end of section A in lesson 1. Today we are going to go on to section B, which is piecewise defined functions. Hopefully you remember a little bit about this from last semester. But piecewise functions is where we have different formulas for different parts of the domain. So we have a picture that's not a smooth curve. We have parts of things stuck together. Well, sometimes they're not even stuck together. There's just two different pieces on a graph. We've got to figure it out. So in example 1, make sure we are all muted, please. In example 1, we have a function, and these are the two pieces of the function. So we are asked to find what is the function at 0. So if x equals 0, essentially, what is y? Find the function at 0. So we go over here to the definition. 0 is smaller than 1, so we must use this side of the equation. So 1 minus 0, 1. If x equals 1, what is y? So looking here, equal to or less than 1, so this would be 1 minus 1 equals 0. And then if x equals 2, we now have to use the x squared function. So this would be 2 squared. As a function, 6 equals 2. Okay, so we're looking at the restrictions of the function, and depending on where x lies, you have to use a different formula to find the y value. Now let's take a look at the graph. If x is less than or equal to 1, so let's say this side of the domain, then we have y equals, I'm going to rewrite this as negative x plus 1. Can you see why that's still true? I just put the 1 and the x in backwards order because I want it to look like y equals mx. So I know that if x is 0, y is 1. Just calculated that. And when x is 1, y is 0. So I have a y-intercept at 1. My slope is negative 1. And I can't go forward to the right because my domain ends there. I can go backwards. Draw an arrow, keep going that way for the first half of the graph. And then if I have x is greater than 1, I have a quadratic. Okay. Greater than 1, I already have a point that I did over here. When x is 2, y is 4. 1, 2, 3, 4. Essentially, this is a quadratic, right? This is a parabola, and I'm going to dot in the shadow, right? This is where it would be if I didn't have that research. So in this function is 2 parts. Half of it is a straight line pointing down, and the other half is part of a quadratic or parabola. Let's take a look at an absolute value function. So, an absolute value function, what does it look like? Do you remember? Yes. What does the equation look like? Big bracket. All right. And yes, you're right. It does look like a V. That here. The absolute value function is probably one of the best examples of what a piecewise function looks like, because really, the real definition here is the square root of x. Right? You have two possible values for the square root of x squared. So this is telling me in an absolute value function that the value is negative x if x is less than 0, and positive x if x is greater than or equal to 0. This is my piecewise function for an absolute value. So if I have a negative 1, that means it's less than 0. So my function is negative 1. I end up with a positive. If my function takes an input for an x value of positive 2, so this is how we define the absolute value function. Whatever your x is, square it and take the square root. It's always going to be positive. Also a reminder, another way to think about it, this is just y equals x, the line, and we're taking anything in the negative, flipping it up to the top. Do you remember this? Find a formula for. I'm going to ask you to draw the graph I'm about to draw. Dot, dot, dot. Actually, you know what? I'm going to do it with a pink pen so then you can actually see it. Dot, dot, dot. Next, dot. And then arrow going. Okay, so this is a broken line function. So I want you to take a second and just visually tell me how many functions do I need to define this? One. Tell me with your fingers. Okay, what would the first equation be? Okay, so between 0 and 1, x is the, or y is equal to x. What about the second piece so far? X greater than 0? No. What are the restrictions? Inclusive or exclusive? No. Look at those lines we just wrote. This piece is this piece. We have an inclusive restriction. So when we write a second function, it can't be, x can't be part of two functions. Okay, so because we have inclusive 1 in the first function, it is a strict inequality for the second function. What about the two? To make this inclusive. Okay, I'm not quite in agreement with what the function looks like.
In function.
Absolute value.
Not quite. Okay, let me do it this way. If I extend this, this is y equals x, but if I extend this, this is not negative x.
Negative x plus.
Negative x plus 2, yes. Or you could say 2 minus x, that would also be all right. So that covers this piece, that's this restriction. So I do need a third one here, right? Because if I continue with 2 minus x, I'm going to continue going down, and this does not go down, it goes straight. So how would I express the last piece of my graph? Okay, and my restriction?
X.
Strict or not strict? Inclusive or exclusive?
X.
Exclusive, yes. We do not include the 2 because the 2 is included in the line above.
Wait, so strict is in exclusive or strict is in?
Strict is exclusive. Okay, does this make sense? No. What are we missing? Yes. Yes, I can. Okay, so do you understand how I drew this picture that I'm currently on? Okay, so in the absolute value function, this line here, this part, represents the line y equals x. Right? But it's only y equals x when x is a large number, or sorry, a positive number greater than 0. And this part is y equals negative x. So it has the same values of x, but it has a negative slope, and it only applies to when x is less than 0. And here you will notice where my restrictions lie. I said that while x is negative, I'm not including 0. And while x is positive, I am including 0. 0 is a defined value. 0, 0 is a point on the graph. It is also okay to write it this way. I could say while x is less than or equal to 0 here and greater than here. Right? I could put it in either one, but whichever one you choose, you cannot put it in both. Okay, we want to make sure that we have clear definitions. Does that make sense? Any other questions before I move on? We're good. All right, let's go to the next example. This is going to be a step function, meaning that it jumps from line to line. Ignore the little triangle on the graph. I'm going to draw one with, again, my pink marker. So what if I have a function like this? I'm going to change this slightly into a word problem, but the idea is the same. Let's say that the y value represents the cost in dollars. And let's say that the x-axis represents the weight in grams. Okay, where each line here is 1, 2, 3. And let's say that each step is a quarter, like 25 cents. 25 cents. This one's 50 cents. This one is 75 cents. And this is $1. Okay, the only reason I'm kind of converting it into a word problem is because I want you to be flexible with notation, but understand the fundamental form. Here, instead of writing my function f of x, I'm going to be writing my cost as a function of weight. I'm simply relabeling it so that it fits my description, but the meaning is the same. So if I were to write the cost as a function of weight, hopefully you see that we have a 3-piece function, and the restrictions are going to be very clear. Do we remember what an empty circle represents? It could be a point of discontinuity, yes? It's excluded from the value, right? So different ways. So it comes close, but does not touch. So it is excluded, excluded. It's a strict inequality. And then this one can touch this point. It is included in our restrictions, included. Okay, so based on this information, what is my 3-piece function going to be? How would I describe this line here? What is the value? 0.25. What is the restriction? between 0 and 1. Oh, and I just wrote an X. I should have a W because it's weight. Between 0 and 1. Okay, and what do my restrictions look like? Correct. 0 is not included, the 1 is. So 0 has an empty hole, 1 has a filled hole. So filled means we can touch that number, empty means we cannot touch that number. Okay, can you see that the pattern would continue with the other 3 lines? Right? So this is 0.5 between strictly 1 and inclusively 2. And then 0.75 between strictly 2 and included 3, and so on. Does that part make sense? Do we recall this or seeing this elsewhere? That was a mixed answer. All right. Well, now it's in your notes, so now you know. Let's go to symmetry. All right. When we are looking at symmetry, we are looking for the function to have the same value, regardless of whether or not the number we put in is positive or negative. So +1 and -1 should have the same value after we put it through the function. This is what we call an even function, and it has to be accurate for all of the possible x values. This is what we call an even function. It's as if the y-axis is a mirror and the left side and the right side are the same. So an example of this would be x squared, right? Left and right are the same. Positive x1 and negative x1 both give you positive y1, right? Another example is if you have cosine graph. Right? Something that looks like this. It's symmetric about the y-axis. The y-axis is like a mirror, same side on the left, same on the right. So here's an example. F of x equals x squared, or x to the 4th, or x to the 6th. Do we see a pattern? Yeah, even powers. The basic functions of even-powered polynomials is going to give you a symmetric or even function. Also, y equals absolute values. That V shape is also symmetric. Y equals cosine gives us a wave where the center of the wave is on the y-axis and it waves out the same on each way or each side. Okay, so it is symmetric about the y-axis. Symmetric about the y-axis. All right, the next part is looking at an odd function. An odd function is, my best way to describe it is like opposites, where when we put the value of negative x versus positive x, the y values have the opposite sign, but the same value. So for example, if I have f of 1 equals 1, and f of -1 should equal -1. An example of this is a cubic function or a quintic function or a, what's the 7? Heptic one, yes. Okay, so here we have symmetry, but it's kind of like a reflection. Let me see if I can draw this graph without making it look ugly. Okay, and here the reflection occurs about the y equals x. Or you can think of it the origin, sorry, not the y equals x, about the origin. So they're on opposite sides essentially. So this would be also like a sine function, right? A sine function starts at 0, goes to 1 and -1. Right? So f of x of a sine function. Okay, so a negative x gives us the same as doing a negative y. Okay, so here I'm going to do another example here. If I have sine x as my function, okay, sine of pi by 2, or sine of 90 degrees. Do you remember what that should equal? 1. Now if I do sine of negative pi by 2, -1, right? So switching the input sign, positive, negative x, also switches the y sign, but the values that are coming out are the same. Any questions here before I move on? Point of symmetry. The origin is your reflection axis there. Okay, some examples. Take a moment with the person sitting next to you. Are these functions even, odd, or neither? Use the test. Here is your test. This is the test for an odd function. This is the test for an even function. So if you change the sign of the x, but the y comes out the same, then it's even. If you change the sign of the x and the y also changes sign, then it's odd. But if you get something weird, then it's neither. So do the test. Okay, so if you look on the screen here, I did the test. Instead of an x, I put a negative x. I substituted into the function with brackets. And I looked at whether I can factor out the negative if it disappears or it stays. And in the first one, I could factor it out, which means if I put the negative x on the inside, I get a negative y on the outside. So that tells me that it's odd. I did the same thing in part B, but the negatives canceled out because I have a quadrat or a quartic there. So I ended up with the same function that I started with. So then that's even. In the last one, notice that this is positive and this is negative. When I substitute a negative x, this one turned out to be negative and this one stayed the same. So you can't change a negative on half the equation and call it something. This is where the result is inconclusive. It's neither. It's not odd, it's not even, it's just a graph that doesn't have any symmetry that we can see. Any questions here? Yes. If you have a function that's even or odd degree that is not shifted, so it doesn't have any plus or minus numbers, right? It's centered about the origin, then you can look at it and say, yeah, that's going to be even or odd. So x squared is even. But if you have x, if you have something like this, I'm just going to do it off to the side here. So f of x equals x squared is even. If I say x squared plus 2, this means I've shifted it up. This is still even. But if I say x minus 3 squared, now I have shifted it to the right. It's no longer centered. So this is neither. It's not going to be symmetric at all based on the graph. So it depends on the shift. If it's up or down from the basic graph, then you can look at it and say whether it's symmetric or not. However, it depends on the function and depends on the graph. That's why we have the test to see what's going to come out at the end. That's a good question. Any other questions? All right. Last part of our notes here is understanding whether a function is increasing or decreasing. I'm hoping this is very intuitive for you, because this is where we're looking at the slope of the graph. Is it going up or is it going down? So we have here a point A, and if I were to sketch we didn't talk about tangents yet. That's all right. If I were to look at the slope at point A, you can see that it is increasing, right? If I looked at this point, oh, that's new. Very cool. I guess they know Valentine's Day is coming up. All right, here is a positive slope. Think of like climbing this hill. If it is a struggle because you're moving up, it is increasing. If it is very easy because you're sliding down, then it is decreasing, right? Going up or going down. At B, what would we call the slope at B? You're at the top of the hill. Are you going up or are you going down? No, what do we call? Yeah, a horizontal slope. So you're not going up or down. What do we call this? Yes, slope is 0. You're not going anywhere, not up or down. Same with C. You are at the bottom of the hill. You are not going up or down. You are at the bottom. This is slope 0, and then you are going up again. So this is where I want you guys to think about interval notation. Interval notation. When we look at domain and range, you could say x between 0 and 5. Or write it as an interval. When you are including a number, we use square brackets, and when you are excluding a number, we use round brackets. Include, exclude. Okay, now if you have something that has multiple intervals, we use the U sign, capital U, but without the kickstand, because that's a little u. This means technically union. You want the real math term, or you can just say it means and. So you could have, for example, an interval that says it goes between 0 and 5, and it goes between 10 and 15. Okay, so take a look here. Can we write an interval notation for where it is increasing? Where is it increasing on the graph? Between A and B. Okay, if I were to write this in interval notation, what bracket am I using for A? Square bracket for A. And when I get to B, what kind of bracket? Round, because at B, it's a flat line. So it's no longer increasing when we get to B. Okay, is there another place that it's increasing? C and D. Okay, so I'm going to say and what's the bracket for C? Round, because at C we are at the bottom of the hill and we are reaching D and it is still going upwards, so we use a square bracket there. Yes, sir. We are not increasing, so we are excluding with a round bracket, right? Round bracket means excluding. We do not include that point, but we're reaching that point. Okay, what about decreasing interval notation? Round B till C. What kind of bracket on C? Also round. And I think that's it. Okay, so a function is called increasing when a consecutive x value is bigger than the initial value. So the value B is at a higher point than the value A, and B is consecutive to A, so it is increasing. And decreasing where the function value is lower than a consecutive or than the previous point. All right. Your homework. Yesterday, you did up until number 11. Today, I would like you to attack the rest of it. If you have questions, please ask. Please stay on task. Please focus and make sure you are asking lots and lots of questions.